This is a very erratic, pulsatile nature of blood pressure. Would you want these extreme changes and these high pressures to be going through a capillary bed? Shred it to bits. So before we get to the capillaries, we want to get rid of this pulsatile nature. We want one even pulse pressure, and we want to reduce it enough where we're not shredding the capillaries to bit. We want to reduce it enough so that we get good time for diffusion, exchange of nutrients and gases and that sort of thing. So your arterioles are called your resistance vessels. Why? They've got a great thick, many layers of tunica media, very little elastic property, so when that blood now finally has to move through them, they're like a vice. And they're getting rid of that pulsatile nature, and they're streamlining that blood pressure so that it's more even-keeled and reduced enough so that the baby capillary beds can handle it. Are you okay with that so far? Okay. So we have metarterioles that are branches off of arterioles that will lead to a thoroughfare channel. That's what this center area of the capillary bed is. We also have circular bands of smooth muscle called precapillary sphincters. Now, any given time, your blood, most of your blood is in your veins, about 70% of your blood. Now let me do another thing. Also, at any given time, not all of your capillary beds are open, meaning getting perfusion, blood traveling through them. This would be a capillary bed that is being perfused. This would be an example of a capillary bed where blood is being shunted through the thoroughfare channel. At any given time, you've got capillary beds that are being engorged with blood and then blanching out because very little blood is flowing through them. This is a type of autoregulation. I will teach it to you, probably I'll get there on Thursday. But you don't want a tissue bed getting too much blood flow. How much oxygen delivery do they need anyway? How many nutrients do they need? So you want some blood flowing through, let the tissue bed take what it needs, but then redirect the blood flow to some other capillary bed. We've got enough supplies. When we go through our supplies, we'll open up the precapillary sphincters and allow blood to flow again. So the tissue bed and how metabolically active it is will dictate those precapillary sphincters to either contract, redirect blood through the thoroughfare channel. That's like the tissue bed saying, we have enough supplies, go on, go somewhere else where you're needed, let us use what we have. Then when the tissue bed consumes the nutrients and uses the oxygen, different chemical signals will be released to tell the precapillary sphincters to relax. And as they relax, now the entire capillary bed will be perfused with blood, and the tissues can take what they need. Don't you think that's very logical? Look, it doesn't make sense, does it? If you start tapping your pinky toe, that's increased metabolic activity in your toe, correct? That muscle serving the toe, or muscles, being more metabolically active is going to need more nutrients, right? More oxygen. Does it make sense to have the heart work harder just for that pinky toe capillary bed? No. Plus, increased workload for the heart means that you are going to likely have more blood flow to other capillary beds and more shear stress. They don't need it. So rather, it's more sensible to have the capillary bed actually release factors, chemical signals, that will tell the precapillary sphincters, yes, we need more blood flow, we need more food, we need more oxygen. Nope, we're good. Shut her down. Redirect. It's genius, right? That way you don't need systemic changes just for a local capillary bed. So I'll be teaching you more of those chemical signals on Thursday. Now finally, we're the capillaries. We see in this picture This simple squamous endothelium, we see a basement membrane known as a basal lamina. It's like a sheet of protein. And around it, we're going to see supporting cells called pericytes. Basically, what this should be screaming to you is we have the fewest layers possible, and this means more readily diffusion rates. So that did not make sense. Diffusion will be better. All right, so what else do we see? We see intracellular clefts. These are gaps in between the endothelial cells. We can have plasma moving through those intracellular clefts. That's going to be a way that we're going to have fluid exchange. But do not dismiss diffusion through the actual cells. From the lumen, through the cell membrane, through the cytoplasm of the cell, out the back door, if you will, the cell membrane, and through the basal lamina. So simple diffusion is going on. There's also exocytosis and endocytosis going on. There's also physical pushing of fluid through the intracellular clefts into the interstitial space. All of that is going on. Are you okay so far? Okay. Your cells have to be within a few, like 20 to 30 microns of distance of a capillary bed. You have about 10 billion capillary beds because you are relying on diffusion. So everything has to be close enough to the capillary bed to get that. Now, did you go to Body Worlds? The first one? There was my favorite, what do you call it, display for Body Worlds was, it was 3 bodies, and you can tell one was taller than the other, and it was supposed to be a husband and wife, and then the dad had a little kid on his shoulders. There were no bones, there were no muscles, there was no nervous tissue, it was just their blood vessels. It was incredible. You saw the elastic arteries, you saw them branch to the muscular arteries, you saw arterioles, but then you saw these little tufts of capillary beds everywhere. Billions of them. It was truly remarkable. And all I can think about was, who picked away all of the other tissue from around those blood vessels? Because I would probably have to shoot the neighbor's cat to do that. I would get so bored. Anyway, it was very, very remarkable. All right, there are 3 types of capillaries. Their anatomy is different. The most abundant, but least permeable of the 3, and be mindful of what I said. I didn't say they weren't permeable. I said they were the least permeable of the 3. The most numerous but least permeable are the continuous capillary beds. By that we mean you have an endothelial cell, a jutting next to another endothelial cell with an intracellular cleft. I like to think of them as paving stones, and they're pretty close together. The next type, getting more, progressively more permeable, will be the fenestrated capillary beds, where you actually have holes through the cell membrane. I like to think of them as a sieve or a colander, so they can allow massive shifts in fluid from the inside of the capillary to the outside of the capillary. Where do you see fenestrated capillaries? Well, they're in sinus cavities, but the most notable place will be the kidney. The glomerulus is a fenestrated capillary. The most permeable but least numerous in the body are the sinusoids. There are large gaps in between the endothelial cells, large holes through their cell membrane, and we see this in the liver. Why is this important? Any blood coming from the abdominal cavity must go through the liver for detoxification. This is blood that is carrying nutrients that you just absorbed, but it could be carrying some sort of intestinal parasite. It could be carrying some sort of toxin that you absorbed, some pesticide, something. So as the blood is going through the hepatic sinuses, these large permeable capillary beds, on the outside of the capillary, you're going to have macrophages. You know, monocytes lead to macrophages. And so as the blood is flowing in the capillary bed, these macrophages have easy access to the plasma inside. And they can phagocytize any bacteria that might be there, or they might be able to phagocytize any chemical. They're participating in detox, and before that blood gets back to the heart, you want your monocytes to have easy access to the blood. So very permeable, but least numerous of the body. So this picture that I have on here, the top left picture that you're seeing is a continuous capillary bed, and the bottom one that you are seeing is a fenestrated capillary. Here's another picture of a fenestrated capillary from another textbook, where again you see these intercellular clefts, but you also see literally pores created through the cell membrane, allowing more filtration, more movement of blood plasma from the lumen of the capillary bed out. Now we're moving back to the veins. The veins are going to be your capacitance vessels. That means at any given time, about 70% of your blood is found stored in the veins. They are called your capacitance vessels, meaning they have the capacity to hold a lot of blood. They're very distensible. They can keep accumulating blood. Veins have unique anatomical structures that arteries don't have. They have valves, and these are going to promote one-way movement of blood. They don't have a robust tunica media. They can't really put a good squeeze on the blood inside to help push it back to the heart. They will rely most often on the skeletal muscle pump. That means as you move and the muscles contract, they will bulge on the veins that are found inside them. And as they bulge, that is going to push the blood more securely. And as you relax your muscles, the blood will backflow, but it's going to fill those cusp-like valves. Again, this is going to help defy the laws of gravity and help return the blood from your lower extremities back up to back up through the veins to the inferior vena cava and back to the heart. Valves can fail, as evidenced by varicose veins. So if you are not moving around a lot, or you're standing on your feet a lot of the blood can pool in those capacitance veins in your legs. That means the valves are getting heavier, weighted down with more and more blood, and they can evert. And then that means the blood will accumulate in the lower section of the vein, and that pressure will build, and those valves will probably fail. So what can we do for varicose veins? Well, we can inject them with a dye so they don't look so unsightly. We can cauterize the vein. We can take them out. Blood vessels will regrow to drain the blood from that area, but you can remove them, surgically remove them, and still have proper venous blood flow. Oh, yes?
You know, when you're on your feet all day, you're standing all day, they say that you should wear like tight stockings or loose stockings.
So compression bandages help push that fluid back up, but when you're standing on your feet all day, what else? Okay, your valves might not be failing. You might not get varicose veins, but I'm on my feet all day. By the time I get home, if I don't do my running before I come to class and I do my running after, it feels like my running shoes are too small. Why is that? Although I don't have varicose veins, I still have that gravitational pull. I still have more blood accumulating in my veins, and it dams up to the capillary beds. This is going to change one of those 4 Starling forces that I'm going to tell you about, and the propensity will be more fluid going out from the vessel and into the interstitial space. I have edema, right? That's why my shoes feel too tight. So even though it's uncomfortable, I know it's good for me to still get some exercise at the end of the day, to be moving around more to help get that fluid come back into the blood supply through the lymph, get it back into my cardiovascular system.
Varicose veins, aren't they?
It can be. So the valves can fail. You can have that predisposition of having weak valves. But it does not necessarily mean that if your mom has varicose veins, you will.